All right, so far in this lecture, we have defined two things. We've defined this concept of outer measure of any old set, given just any old class of sets that contains the full set and any old non-negative function. We've defined outer measure as a certain infimum of sums of mu's of things. And then we've used that to define the concept of a mu measurable set, which typically, under these circumstances listed here, which are usually circumstances that hold, typically this will be an enlarged version of our original class of special sets. So this is a larger class of sets. And we've stated some basic facts, and we have yet to prove fact number 3 here. And again, fact number 3 is not actually something we're going to use that often, or at all maybe. I'm basically just including it as sort of a buffer between big theorems that we have to prove, mainly for practice. So this is something where getting the practice by going through the proof is probably more important than the result itself. So proof of 3. Let me get my assumptions down. A is just any old collection of subsets of X. It contains X. Mu is any old non-negative function on A, and that's it, right? Okay, now let's let B be a subset of X. Then I have this if and only if to prove. So let's start working on the left implies right. So assume that B is not really any old set, but a mu measurable set. Okay, so that's a certain for all epsilon kind of condition. For all positive epsilon, there's a special A such that this thing happens. That's our assumption. Then what I want to prove is this other for all epsilon condition, the one stated here. So for the sake of proving that, let epsilon be greater than 0. Now let me make use of the for all epsilon condition that I have. It tells me that there's some special A such that mu star of the symmetric difference, B symmetric difference A, is less than epsilon. And I can put any positive number I want here, but I choose to put epsilon actually. So we'll see that choice of epsilon works. Now, how might we find sets D and D prime such that B is a special thing with D thrown in, D prime deleted, and with the outer measures of D and D prime being small? How can we do that? Well, here's a picture. So let's say this is B, and this is A. So just a Venn diagram. Then can I view B as something I get by starting with a special set? Well, I have a special set in hand. A is a special set. So can I view B as A with something unioned in and then something deleted? Well, yeah, I think I can. So start with A, then union in this, then you would get everything, right? Then what should I delete in order to be left with B only? Well, then delete this. Right? So how about I take that to be my D and that to be my D prime? And you know, D union D prime looks like that is the symmetric difference, which has its mu star being small. So that seems pretty good. That seems promising. So let D be B delete A, and let d prime be A delete B. Then let's see, do we really have, like the picture seems to suggest, that B is this? Then I think B is A union D delete D prime. Do we really have that? So this will be like a Math 8 style set theory proof, and you should just pause and verify it. Chase some elements. If let X be in B, make sure you can show it's in there. Let X be in there, make sure you can show it's in there. Okay, so this should work. Okay, and it still remains to verify that mu star of D and mu star of D prime is small. But what we know is small is the symmetric difference, right? And the symmetric difference by definition is just D union D prime. So mu star of D, now remember from part 2 of this proposition, if one thing is a subset of another, then you get a corresponding inequality for outer measures. By the way, this is called monotonicity. So we say this is monotone. That's just a word for preserving order. In this case, the order under inclusion of sets is preserved by mu star and becomes this ordering of real numbers. So due to part 2, since D is a subset of the symmetric difference, we have this. So this is by part 2 of this proposition, and the fact that D is a subset of the symmetric difference. And this is less than epsilon. And similarly, this is also less than epsilon. Same idea. D prime is also a subset of the symmetric difference. So, no square yet. That proves one direction of our proposition. So we've proven this condition. We have found D and D prime with small outer measures. Now for the other direction. So assume, let's give that condition a name. So let's call this condition. Let's call it lightning bolt. I just chose that because I happen to choose yellow, so it fits. So assume lightning bolt. So this is a property of B that we're assuming. And what we need to prove is that B is mu measurable, which is also a for all epsilon type condition. So let epsilon be greater than 0 for the sake of proving that B is mu measurable. And let's use lightning bolt to get some special A and some not so special D and D prime. But still kind of special because they have small outer measures. And I can make them as small as I want. I choose to make them smaller than epsilon over 2. And such that my original B that I started with, remember B is just some random subset of X, and I'm trying to show that if B satisfies lightning bolt, this condition, then B is mu measurable. So B is my special set A with this small set thrown in and a small set deleted. Now our claim is that the special set A works for proving that B is mu measurable, meaning if you take the symmetric difference B with A and take the outer measure of that, then that's less than epsilon. So that's our claim. If we prove this, then for arbitrary epsilon we have found a special A such that mu star of the symmetric difference is less than epsilon. that's the definition of B being in the set A mu. This is the definition. So it remains to prove this claim here. Now, I want to prove two things. Two kind of, quote, easy set theory things. So first I want to prove that B, so remember, the symmetric difference is a union of B delete A and A delete B. So I want to prove that B delete A is contained in D and A delete B is contained in D prime. And all I know is this relationship among B, A, D, and D prime, this relationship here. Okay, so this is again one of those like Math 8 kind of things where you just do it. But let me see if I can make a picture to make it feel right at least. So let me draw in sort of the three sets that we have being combined in different ways here. A, and then D gets added to it, and then D prime gets deleted from that. And then that's supposed to give us B. So in this picture with the three disks A, D, and D prime, where's B? B would be A, then union D, then take a, so imagine now the union of these two disks like that, that's A union D, and then take a byte out of it, so cut out D prime here. So you should get this. So that's B in green. And then what's B delete A? So let's underline that in red. So B delete A is this green thing, and then cut out of it A. So what would you be left with is this stuff. And you can see that that really is a subset of D. So good, check. And of course it'd be better to do like an actual proof, right? But in some sense, if you have only three sets around, then when you just look at a Venn diagram, that's really kind of a way of encoding a giant sort of inefficient proof by cases, but it really is efficient because pictures are easy to prove things with. It's easy to visualize what to do. So I think of this as a big proof by cases, right? Like you're focusing on whether things are elements of all the different little subregions here or not. Those are all like different cases. So I count 7 subregions here, and then maybe you can count the outside as another one. So eight total regions. There are like 8 cases regarding for any given thing, whether it's in or not in any of the given sets A, D, and D prime. Yeah, okay, anyway, so that's the reason I consider it to be a proof when you've got just 3 sets around. So let's look at this and put this in blue. So what's A delete B? A would be this white circle here. And then, yeah, right. Yeah, A is this white circle over here. And then delete B, so look at all the stuff that is in this white circle, but not in the green region. So that would be the stuff here. In the white circle, but not the green region, and indeed that's a subset of D prime. Okay, so good. So now B symmetric, so remember our claim is going to be that the outer measure of B symmetric difference A is less than epsilon. Well, B symmetric difference A is the union of the red and the blue, right? And now we're seeing that that's contained in the union of D and D prime. So B symmetric difference A is red union blue is a subset of D union D prime. And we know that the outer measure of d and the outer measure of d prime are both less than epsilon over 2, right? So then the outer measure of the union is also small? Okay, well, there's something to prove there. Remember, the word outer measure, we call it an outer measure, but that doesn't mean it's a measure. Yeah, if we knew it's a measure, then we could say that the measure of this union is, then it would be finitely subadditive at least. So the measure of this union would be less than or equal to the measure of this plus the measure of that. So there's something to prove here. So we do have, by part 2 of what we're currently working on, the monotonicity of mu star, we do have mu star b delta a is less than or equal to mu star of d union d prime. But this, how do we work with this now? So now we need mu star d union d prime less than epsilon, and then we will be done. What we know about is mu star of d and mu star of d prime individually. So this is what you're about to see is another reason why I wanted to prove this proposition here, is that this portion that we're working on now is going to be good practice for an upcoming lemma. So this is what we're working on now is actually going to be, working with mu star of this little union is going to be a simple version of what we'll do soon, where we look at mu star of a countable union. Okay, so let's see if we can somehow make use of the things we know about d and d prime. We know that mu star of d and mu star of d prime are both less than epsilon over 2. That's part of the definition. That's like how we got d and d prime. We got them so that this happens. Okay, well, mu star d, remember the definition? Mu star is an infimum. So it's a greatest lower bound. So if you have something greater than a greatest lower bound, then some element of the set that you're taking the infimum of will be less than that number. So less than epsilon over 2. So there is some a sequence an in fancy A such that, okay, I'm going to need more room here. There's some sequence an in fancy A such that it covers D, so union of the ANs contains D, and such that if you take the infinite series of mu of ANs, then that converges and is less than epsilon over 2. So, and this series of mu of ANs from n equals 1 to infinity is less than epsilon over 2. Okay, when I make this statement, that includes the assertion that the series also converges. All right, and we can do the same for d prime. So let me just copy and paste this. So we can do the same for d prime, except for d prime, let me call the sequence A prime, covering d prime, so that this is less than epsilon over 2. So remember, now our goal is to try to show that mu star of d union d prime is small, right? We want mu star of d union d prime to be less than epsilon. So one thought that might occur to you is, well, we're unioning d and d prime, so how about we union these things in the cover? So you might think to try an union an prime, and then look at this family of things. But that's a bad idea, because remember, fancy A doesn't even have to be closed under unions here. it really could be any old set. Fancy A is just any old collection of subsets of X. So doing this is not going to help. Rather than unioning the individual sets an and an prime, what we really should do is union the families. So look at the ans and an primes together. Now each of them is a countable family of things in Fancy A. If you union two countable families, then you should get a countable family. But to make sense of a series, it's not enough for it to just be a set. It should be written in some order. Although here the order doesn't matter, because we're talking about sort of non-negative series, so whenever you get convergence, it's absolute convergence. Still though, I want to write things in a certain order because I want to be able to reason about what the series converges to. So my goal now is to combine these two sequences of sets to get another sequence of sets that gets all of them. So how can we do that? Like we have a sequence of sets that goes A1, A2, etc., and another one, A1, A prime, A2 prime, etc., and you want one sequence that gets all of them. You've probably done this before, something like this before. Just alternate. So take this one, and then this one, and then this one, and then this one, and so on, alternating. So instead of fiddling with explicit indexing, let me just do it like this. Let's say let an prime prime, a third sequence in Fancy A, be, and let's let it be this sequence, A1, A1 prime, A2, A2 prime, etc. So that should achieve what we want. Then definitely, let's see, what does an prime prime have to do? It has to, looking back at the definition over here, I want it to be a sequence of fancy sets, of special sets in Fancy A, and I want it to cover my thing. What's my thing here? D union D prime. I want it to cover that. And I want the series to converge. So those are the things that I want. So this is a sequence in Fancy A. Good. And if I take the union, then that definitely contains the union of the ANs and the union of the AN primes, right? So that contains D union D prime. So it definitely covers D union D prime. Also, let's now look at the series. Does the series converge, and does it converge to something less than epsilon over 2? Because if it does, then I'm done. Then I've got my upper bound on mu star D union D prime. So I need to look at partial sums of the series. So the series, n equals 1 to infinity, of mu an prime primes, that's the series I need to be thinking about. That's equal to, if the series converges, then it would be equal to the limit of the sequence of partial sums. That's the definition of what a series is, right? So limit as capital N goes to infinity of the partial sum up to capital N. All right, so I'm going to write down a bunch of things that are all true if certain things happen. So like this series equals this limit if this limit exists. And then this limit equals this limit if either of them exists. So I'm going to take the limit from 1 to 2 capital N to make things easier to write. And I can always take a subsequence here and focus on a subsequence instead. Okay, that's not always true for arbitrary sequences, but for a sequence of partial sums of a series whose terms are non-negative, this works. The basic principle is this sequence, with capital N as the index, the sequence of partial sums, since these terms are non-negative, the sequence of partial sums is a monotone increasing sequence. And anytime you have a monotone sequence, then having a subsequence converge is equivalent to having the sequence converge. So here I'm looking at a subsequence of the sequence of partial sums to make things a little bit easier to write. And this, finite sums can be reordered freely. So I can write this as sum from n equals 1 to n of these by a suitable reordering, right? So this is just properties of finite sums. Okay, and again, this is true if the limit exists. So hopefully at the end of this calculation we'll find that we have a limit that does exist, and then that will justify things. Now, if the so this is a limit of a sum, right? And that's equal to the sum of the limits, assuming the individual limits exist. Okay, and this is a typo. For some reason the prime ended up on the mu there. Okay, so this is true if these individual limits exist, then they equal this limit. And then because this limit exists, it equals this one because it's a monotone sequence, and then that's the definition of the series. So do these limits exist? Yes. These are by definition, these are the series, right? Which we have, these series converge. And furthermore, we have that they converge to something less than, this one converges to something less than epsilon over 2, so does this one. Whew. Okay, so finally we have convergence at this step, right? So because these limits exist, then this one does, then the argument propagates backwards. Okay, maybe I shouldn't put the box yet. Maybe I should just say a little bit more here. So here, thus mu star of d union d prime, mu star of d union d prime is the infimum of a certain set of real numbers, and here we see that this is one of those real numbers, and it is less than epsilon, right? So this is less than, this is the infimum, so it's less than or equal to this thing, which is less than epsilon. And I think we are done, because remember, we were trying to show mu star of this symmetric difference is less than epsilon, but we showed that it's less than this thing, which we have now shown is less than epsilon. So we are done proving this proposition. Now, something very interesting happened in this proof. So remember, mu star is defined on just the collection of all subsets of X. Any subset, you can talk about the outer measure of that set. And it looks like inside this proposition we have a little proof that mu star is finitely subadditive. Let me see if I can start it at the right place. Basically here, if I, instead of focusing on epsilon over 2, instead of focusing on the fact that these series are bounded above by epsilon over 2, focus on the fact that these series are bounded above, do focus on the epsilon. So, let me put it this way. Let's say epsilon is arbitrary. Then it's too hard to rip it out of this proof. Okay, well, you either see it or you don't, I guess, but it's not directly in there, I guess, but somehow built into this proof, there does seem to be an argument that mu star of D union D prime is bounded above by mu star of D plus mu star of D prime. This proof is focusing on a special case where mu star of D and mu star of D prime happen to themselves be small. But even if they weren't small, you could still sort of add epsilon over 2 to each of them and then carry out this kind of argument, and you would have yourself a proof that that mu star of the union is bounded above by the sum of the mu stars. So we pretty much went through the steps of proving this fact here. Now that's, I think that's quite remarkable, because mu star was really built out of garbage information to start with, like A just being any old collection of sets, and mu just being any old function on A, non-negative function. It's really just nothing that you're starting with, and then we built this mu star, and it seems to have this property. It does, and in fact it has more. So this implies that it's finitely subadditive, right? Because you can iterate inductively and say mu star of any finite union is bounded above by the sum of the mu stars. But in fact, mu star is countably subadditive. Even starting with this like nothing information to begin with, the mu star, the outer measure that you build in this way, is countably subadditive. I really find this to be amazing. But still, pay attention to the sub in subadditive. It's countably subadditive. You get this inequality. This is much, much weaker than saying it's additive. Additive means you get equality in the situation where the union is a disjoint union. In fact, even if we improve the starting data that we build mu star out of, even if we say that mu is countably additive to begin with, the mu star that you build need not be even finitely additive. So let me show you sort of the good news and the bad news. Here's the good news, and this is something we'll probably prove next time. I think this lecture ran too long, but this is the good news, and this will be a fun one to prove. But the bad news is that mu star need not be additive. It need not even be finitely additive, even if you have a good mu to start with, like mu even countably additive. So let me end this lecture with an explicit example. So let's say X is just a 2-point set, 0 and 1, and let A be this sigma algebra. This is one of the most trivial sigma algebras you can have. And it consists of 2 out of the 4 possible sets it could have had. And then let mu be this non-negative function which turns the empty set to 0 and the full set to 1. Then I claim mu is countably additive. And there's really not that much to check here. So countably additive, you need to consider any situation where you have a countable family of disjoint sets in A. Okay, you could take X, or you take X and the empty set. That's pretty much it. Or just the empty set. And in all of those cases, the sum of the mu's is going to be the mu of the union. But I claim that if you take mu star, which will be on the entire power set of X, which consists of 4 possible subsets of this 2-element set, if you take mu star, then I claim that it's not even finitely additive. So look at mu star of the full set, x, that's 1. So you see that it's not finitely additive. These are two disjoint sets, these two singletons. Their union is this, but the mu star of the disjoint union seems to be strictly less than mu star, than the sum of the mu stars. So what actually went wrong in this example? How come we went from mu to mu? This seemed like a harmless setup, right? I feel like assigning the value 0 to the empty set and the value 1 to the full set, that sounds like a pretty reasonable way to set up a measure for like probabilities or areas or whatever. That just sounds like a sensible way to go. So how come things went so badly when we went to outer measure? Is outer measure just a terrible construction? No, I wouldn't say that. And I also wouldn't say that mu is choosing bad values here. I would say what leads to the problem here when you try to use outer measure is that it's not that mu takes on bad values, but that mu doesn't take on enough values. It does not take on enough values. This a is too small. So mu star is ending up just not being so good. And one way to look at it is that even though mu star ends up being defined on all subsets of x, it's really only very good, it turns out, when you look at mu measurable sets. So if you want, you can think about what are the mu measurable sets in this example. Actually, how about I make that the quiz for today? Think about what are the mu measurable sets in this setup. What would a mu be?